So only one person decided to come back. So in this lecture, we will discuss the second case of non-stationarity, which is called brakes. This is more or less understandable thing. Again, we will start with the introduction, just to remind ourselves what is stationarity again and again. That stationarity is such feature of a time series when the probability distribution of a series doesn't change over time. So when we take some interval of time periods and kind of at every moment we observe the random variable, then the joint distribution of variables within this interval are not going to change. Doesn't matter which interval we are taking. Kind of the weak stationarity condition requires that expected value and variance do not change over time, and the autocorrelations of the same lag stay constant. Last lecture we spoke that when time series is not stationary, then all hypothesis tests, confidence intervals, forecasts are not reliable. You simply do not have a right to use them. And we also listed two types of non-stationarity, trends and brakes. So now we will talk about brakes. What is a brake? Brake occurs when the population regression function change over the course of the sample. So basically, your series were following one particular model, and then at some moment of time, the model changes. Something else changes, right? So the population regression function changes. This may happen because of changes in economic policy, changes in the structure of economy in specific industry, in environment, some decisions made by politicians or some other decision makers. Well, basically, so time series are not kind of independent of the process of the mechanisms that underlie this time series. So that is why in the fundament of series there are some processes, some actions, some decisions, and when something changes in this in the basic thing, then of course the series themselves also change. We also can list two types of brakes. So one type is a discrete change, when the population regression function changes abruptly at some distinct date. And we can also observe some gradual evolution of the coefficients over a longer period of time, when when the change takes some longer period of time. It doesn't happen at one specific moment. Well, we will talk about one specific example of a structural brake that we have seen in the first lecture of about time series, when there is some major change in macroeconomic policy. So, for example, in 1972, the Bretton Woods system of fixed exchange rates was abandoned. And before this year, the exchange rate of United States dollars to Great Britain pound was almost constant. And after 1972, the exchange rate started to fluctuate. So we can see this on the graph. So there was an almost constant rate up to 1968. Then there was a devaluation down to something like 2.3. But still, at this period and this period, we see that the exchange rate is almost constant. And then something happens, and you can observe kind of wide deviations of this exchange rate, going down, going up, and so on. So clearly something happened, something that produces this series, and this something is explained here. So the Bretton Woods system was abandoned, and instead of constant exchange rates everywhere in the world, where the floating exchange rates were introduced. Well, why this matters? When we apply any type of linear model, OLS regression will estimate a relationship on average. Well, but the average here and average here are two different averages. And of course, we do not have a right to apply OLS for the whole period of observations here. The estimates would combine two different periods, and the average function, well, will be different from the true regression function. Will be far away from the true regression function. And when we poorly estimate the relationship, we will have poor forecasts, and poor forecasts lead to poor decisions made based on these forecasts. So that's why we need to take into account somehow this this fact of a structural break. Well, there are two types of breaks, as we spoke. One type when we know the date of a break, and another when we don't know the date of a break, because probably we simply don't know about it, or probably there is a gradual change from one system to another system, and we cannot simply identify which moment separates two periods. So the first is simple. When we know the exact date of a break, we can introduce a binary variable. And well, this is again similar to the first course in econometrics, when we applied dummy variables or binary variables and their interactions. For example, if we consider AR1 model with the intercept and a single leg, and we have a date, tau, where there is a break, we can introduce the dummy variable or binary variable dt of tau, which equals 0 before the break and 1 afterwards. So this is going to be our binary variable. dt of tau is 0 before the break, including the date of the break, and 1 afterwards, after the break. And the regression function will be the following. So we will have a usual AR1 model here, and we will have this gamma 0 times dummy variable, which is gonna be 0 before the break and which is gonna be 1 after the break. So gamma 0 times 1 is gonna be phi 0 plus gamma 0. So the new intercept will be phi 0 plus gamma 0. And also the new slope will change, right? Instead of phi 1 after the break, this is going to be phi 1 plus gamma 1. So here is the model, and how we can test if there is a break or not. If there is no break, then the population regression function is going to be the same over both parts of the sample. So the null hypothesis is that gamma 0 equals 0 and simultaneously gamma 1 is 0. So these two coefficients simply 0. Then at tau there is no break, and we can apply the same regression function to both periods, pre-break, pre-hypothesized break, and after hypothesized break. Under the alternative hypothesis, there is a break, and the population regression function will be different before and after the break. And in order to test this joint hypothesis, we know that we have to use f-statistic and f-test on this joint hypothesis, that two coefficients simultaneously are 0. And in the case of time series, we often call this test a child test after the author who first proposed this type of test for the structural breaks. So now, going to our example. When we observe the time series of exchange rate of British pound to dollar, we have two dates of possible breaks. One date is November 19th, 1967, when the devaluation happened from 2.8 to 2.4, and January 1972, when there is a breakdown of the Bretton Woods system. So we will estimate the regression with two dummy variables, d1 and d2. d1 is going to be applied to the first suggested date of the break, and d2 is going to be applied to the second date. So d1 is going to be 0 for t, which is smaller than 1967 12 months, and 1 after December 1967. And d2 is going to be 0 before January 1972 and 1 after January 1972. So M12 means month, so December. So here is the regression output. So first of all, note that r squared is almost 1, which means that we fitted model almost perfectly. Now, here are the coefficients. So probably, well, let me see. Yeah, let's kind of decipher them one by one, because maybe from the table it would be difficult to comprehend what's going on here. So our estimated model yt hat equals to, so there is minus 379 plus yt minus 1, so the past observation of yt, multiplied by 235. So this is the coefficient on the lag exchange rate US UK. Then we have d1, and the coefficient on d1 is 3.2 times d1. Then we have the interaction term, so minus 1.1, 11, let's say, times the interaction, which is d1t, d1t times yt minus 1. And the second part, which is 0.61 d2 t minus 0.26 times the interaction term d2t times yt minus 1. So again, we know that d1 equals 1 after December 1967. D2 and 0 otherwise. So D2 equals 1 after January 1972. 1972. Which means that for the period before December 1972, 67. Our regression function will look like this. Simply this part. Why? Because D1 is 0. D1 is 0. D2 is 0. And this is 0, 0, 0, and 0. So everything is 0. So for the period before December 1967, we have all zeros here. Now, for the period between January 1968 and January 1972, we know that D1 is 1 and D2 is 0. So our regression function will be different. Allegedly, we have not tested the hypothesis yet, but allegedly it's going to be different. So now we have this 3.2 times 1, because D1 is 1, minus 111 times 1 times yt minus 1. And now, after opening the brackets and multiplying by 1, what do we have? We have minus 379 plus 3.2, which is minus 0, 59, plus, well, yes, 235 minus 111, so this is going to be 124 yt minus 1. Well, we have completely different model for this period. And now for the period after January 1972, both variables, both binary variables are ones. So we have to write down everything here. So these, and also plus the rest, 0.61 times 1 minus 0.26 times 1 times yt minus 1, which is now gonna be, so we know what is gonna be the first part, minus 0.59 plus 0.61, this is gonna be 0.02, and 111 minus 0.26, 111 minus 0.26, this is gonna be 0.85 yt minus 1. So this is going to be a new regression function for the third period. So basically these results are listed also here. So I just explained you how did we get the results. Must be similar, right? Probably I've made a mistake somewhere. 124, and after well, this is something strange here. 0.98. We have 85. Yes, because this is my mistake. This must be 124 minus 0.26. Yeah, 0.98. Yeah. 235 minus 111 minus 0.26, which gives us 0.98. Yeah, so these are the three different models for three different periods. But now, when we test the two hypotheses, we know how to test the joint hypothesis in Python. This is simple. You've done this many times. So F statistic for the first hypothesis, that gamma 0 equals gamma 1 and equals 0. So p-value is far less than 5%. So we reject the hypothesis that both coefficients are 0. There is a break at the first date. F statistic for the second hypothesis is also less than 5%, so there is a break on the second date. So both joint hypotheses are rejected. There are breaks in the series of the exchange rate of dollar to pound in December 1967 and January 1972. So finally, we can model three different periods, three different series for three different periods, and I showed you how we can derive the coefficients for all three models. Pre-1967 December, between January 1967, 68 and January 1972, and after January 1972. So, and what is the most important thing here that we can observe? First and second periods are non-stationary. You see that coefficients on yt minus 1 and coefficient on yt minus 1 here, they are greater than 1 in absolute value. So these are non-stationary things. And basically these coefficients are, if you look at the output, where is the output? Look at the output, they are significant, so they are non-zero. So basically, so we need to treat them as probably random walks. But the third one is stationary, close to being 1, but still, this is exactly the case that I told you about in the end of the previous lecture, that we can sometimes have the coefficient which is close to 1, but not 1 exactly. And this would behave similarly to unit root, to random walk model, but it is not. So now, the second part, when we don't know the date of a break. When we don't know the date of the break, the situation is more difficult because, well, we need to guess. And we start with the following approach. We need to come up with the idea that a break occurred somewhere between two dates, tau 0 and tau 1. And we can modify the Chow test in such a way that we are testing for the breaks at all possible dates between tau 0 and tau 1. So basically we need to do something like a grid search. For every date we need to perform Chow test and see what's going on. So, and we are looking for the largest F statistic, and this largest F statistic is going to be used to test for a break at an unknown date. So this type of test is called quant likelihood ratio test. So the statistic, this maximum of F statistics, is called QLR statistic, and sometimes it is called subval statistic. So let's see how it works. So again, QLR statistic is the maximum of F statistics. The distribution of QLR is not going to be the same as for F statistics, so we need to use the specific values of the specific critical values of QLR statistic. And it depends on the number of restrictions that we test. So the number of restrictions is exactly the number of coefficients that we assume to be 0. And also this distribution depends on the time window. So tau 0 over t and tau 1 over t. So in practice, we compute QLR statistic over a trimmed range of the sample. So we take 15% initial observations out, we take 15% of the final observations out, and this range of kind of 70%, which is in the middle, we search for a break between them. And the critical values can be taken, for example, from the Stock-Watson book. So again, these critical values do not follow F statistic, F distribution, T distribution, normal distribution, no. The critical values are specific ones. They can be found in some textbooks or on the internet, but kind of they are not just available from Python, for example. So let's use this method for structural breaks between the interval of December 67 to February 2009 for the same series of USD to GBP exchange rate. So here are the F statistics. So basically, look what I was doing, and you will see this in the exercise session. You can get it from the script lecture 14. For every date within this period, I was doing the same chow test as we did previously here. So here we knew what is the date of a break, and we introduced these dummy variables and we computed everything. So here, and we tested the joint hypothesis. So now I was doing completely same thing, but I was taking every date within this time window. So there are a lot of dates every month. I was creating the dummy variables, estimating the OLS regression, testing the hypothesis, the joint hypothesis that coefficients on dummy variable and interaction term both are 0. And computing F statistic from this test. And here is the graph of F statistics. And you see that F statistics are very large around 1977 and also around 1985. So they are the most largest. And also here, which is exactly, we know that there was a structural break, there was a devaluation. What is interesting that nothing happened in 1972. So QLR statistics is 15.14, which is associated with the date of devaluation. And the next largest F value is associated with February 1985 here. But nothing happened in January 1985. So I was searching the internet what has happened here. So maybe there was some change in the policy. Well, if we observe the series of the exchange rate, going back there. So what is 1985? It's somewhere here. So the exchange rate reached its minimum at this date. So probably the algorithm itself captured that pre-1985 there was the long period of decreasing in the exchange rate, and then something else happened. So there is a break, but this break is not caused by any change of economic policy or like exchange rate policy or something like that. So basically with this approach we confirmed one date of the break when the devaluation has happened, but we didn't confirm the second date of the break because F statistic there is not that large. Well, might be, but other dates are suggested also as potential dates for the break. So now to conclude with the breaks. If you know the exact date, a specific date of a break, then we can detect you can detect this with QLR statistic. If you don't know the date of a break, but if the break happens at the specific date. we can estimate the regression function simply using binary variables. So this is the familiar approach from Econometrics 1. And if there is a distinct break, then we can apply the inference on the regression coefficients as usual. And forecasts are also applied from the last regression function, which is applied to the end of the sample. Of course, the first part doesn't matter, so it's just for, I don't know, some historical modeling, but not for forecasting. So this is all about breaks. Questions? Mordok, Khan, any questions regarding the breaks?
No, no questions.
Well, then the last remarks regarding the course. So first of all, do the self-study on non-stationarity breaks. So the self-study is available on the course page somewhere here. Yeah, trends and breaks. Basically, you can do both. So don't look at the date. So this date is not correct. So the self-study is available all the time. Doesn't matter. And there is the last home assignment number 8 on the non-stationarity cases, trends and breaks. So this home assignment is going to be available from December 1st, so next week, because you have a lot to do this week, quizzes, home assignments, and it's going to be available 2 weeks until the end of the semester, until December 15th. So with this lecture, we conclude everything for the lecture part. So basically, my job is done, almost. The last thing that I owe you is to give you the preliminary results from midterm and home assignments and quizzes. Since there are some works in progress, some quizzes are in progress, some home assignments are in progress. So after you finish everything on December 15th, till December 19th at latest, I will distribute you your preliminary results. So home assignments, quizzes, midterm together. The exam is done not by me. The exam is done by Klim. It's gonna be done by Klim. So the exam date, the exam rules, the exam requirements are gonna come from his side. If over this period, if over the next 3 weeks, you have some questions, problems, suggestions, anything else, let me know. You can contact me via the course page, and we can set the meeting, or I don't know, if I can answer your question in the written form, I will do that. So otherwise, thank you for your attention and your patience over this semester. It was nice working with you. So we did 14 lectures overall. So hope that this material would be useful in your future career.